Hey there, science fans, Bill Nye here, and today we're diving into the exciting world of electric charges. You know, those invisible forces that make your hair stand on end or give you a zap when you touch a doorknob. It's all thanks to something called Coulomb's law. Ever wonder how these charges interact? Why sometimes they attract and sometimes they repel? Well, it's all about the forces between them. Just like gravity pulls you towards the Earth, electric charges have their own set of rules for attraction and repulsion. Get ready to unlock the secrets of electric charges and the forces that govern them. We'll break down Coulomb's law, explore how to calculate these forces, and see how it all plays out in the real world. So buckle up, because we're about to embark on an electrifying adventure. Let's get started. Coulomb's law is like the rulebook for electric charges. It tells us how strong the force is between two charged objects. Think of it like this. Imagine two magnets. You know how they either stick together or push each other away? Coulomb's law helps us figure out how strong that push or pull will be. Here's the formal definition. Coulomb's law states that the force of attraction or repulsion between two-point charges is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. Now let's put that into a neat little formula. Don't worry, we'll break it down. This formula might look intimidating at first, but it's actually pretty straightforward. It tells us that the force F between two charges, Q1 and Q2, is determined by the amount of charge on each object, Q1 and Q2, the distance between the charges, R, and a constant value called the Coulomb's constant, K. We'll explore each of these components in detail in the next section. Get ready to unlock the secrets of this electrifying formula. Let's break down that formula and see what each part means. First up, we have the charges, represented by Q1 and Q2. These charges are measured in a unit called coulombs, C. Think of coulombs like buckets of electric charge. A bigger bucket means a stronger charge. Next, we have the distance between the charges, represented by R. This distance is measured in meters. But just like with magnets, the closer the charges, the stronger the force between them. Finally, we have the Coulomb's constant, represented by K. This constant is always the same and helps us tie everything together in the formula. It's like the magic number that makes the equation work. So the formula tells us that the bigger the charges, Q1 and Q2, the stronger the force, F. More charge, more force. The closer the charges, smaller r, the stronger the force, F. Closer together, stronger force. Now that we understand what each part of the formula means, let's see how we can use it to calculate the actual force between two charged objects. Get ready for a shocking example. Let's imagine we have two socks fresh out of the dryer. They've been rubbing against each other and have built up static electricity. Let's say sock number 1 has a positive charge of 2 coulombs. We'll call it plus 2C. And sock number 2 has a negative charge of 1 coulomb. We'll call it minus 1C, and let's say they're 0.1 meters apart. Now, let's plug these values into Coulomb's law. F equals K times Q1 times Q2 divided by R squared. F equals 9 times 10 to the 9th Newton meters squared per coulomb squared times 2 coulombs times minus 1 coulomb divided by 0.1 meters squared. F equals minus 1.8 times 10 to the 12th newtons. Wow, that's a huge force. But don't worry, in reality, the charges on our socks would be much smaller and the force wouldn't be nearly as strong. This example just shows us how the formula works and how different factors influence the strength of the electric force. Now that we know how to calculate the force, let's explore the direction of this force and how it determines whether charges will attract or repel.